Hi, in this video we will use our simple model for color image to make inferences on images. We will start with the specularities, or also called highlights. Specularities have a substantial effect on human perception, giving us information about the material of an object. Also, highlights usually saturate cameras, and because the operation range of cameras usually covers the dynamic range of albedos, we can assume that small saturated patches are specularities. So, under specific situations, we can easily find those white patches to be marked. Another alternative is to use the RGB color space. The color of a solid shape is represented by a point in the RGB cube. For a three-dimensional object, we will see a line. That line travels from the origin in the direction of the color of the object. The darker colors will be close to the origin and the brighter will be away from it. Specularities create a plane-like cluster at the boundary because points are a weighted combination of the two different colors, the color of the object and the color of the specularity. This new plane is formed by the line of the diffuse term and the line of the specularity. The latter does not need to cross the origin. Then, if the camera is saturated, the specularity line will hit the end of the RGB cube and then will be clipped. If you find this pattern, then all the pixels in that line are specular pixels, and the specular and diffuse components can be estimated easily. Let's see another example. One way to find the edges on images is by looking for fast changes on albedo. For example, in this image, the albedo of the image drastically changed on the edge of the circle. These changes can be used to identify the different shapes of the image. However, this technique fails on shadows, especially on images from outdoors, when the sunlight creates high differences on the brightness. For humans, this is not a problem. Most of the time, we can clearly know that a dark region is not a different object. To solve this problem, one might assume that, at a shadow edge, there was a change in brightness but not in color. But it turns out that this is not the case for outdoor shadows. Remember that in the outdoors, we can have sunlight that is coming directly from the sun and skylight, that is the scattered light from the atmosphere. So when you take a picture in the park, the subject in the image is lit by both the sunlight, that usually is yellowish, and the skylight, that in a clear day is more bluish. On the other hand, the shadow only receives skylight. Hence, a shadow does not change the brightness alone. It also changes the color of the area inside the shadow. We can use this difference in the color of the light source in our advantage. Each light source has its own temperature and therefore its own color space. Imagine that two different surfaces have certain values under the sunlight, and the same two surfaces have other values under the skylight. We can find the color space for each color temperature and draw a perpendicular line from the plane to the origin of the RGB space. For each temperature, we can measure the distance to the origin over the corresponding line. The result will be a grayscale image where the gray level does not change inside the shadows. So now, any edge that appears in the original image but doesn't in the invariant image is a shadow edge. So now we can use a brightness-based edge detector and then integrate the color inside the shadow area. Okay, in this video we talk about two examples in which we use color to identify regions on an image. I encourage you to read a bit more about any of the topics of this and the previous week. I know that you might want to start to do more practical stuff, So next week we will start the computational part. See you then!